All right, so we are looking at section 2.3 today. First half of this section, 2.3 is page 84. Page 84. We looked at section 2.2 to give us an intuitive understanding of limits. We were just flat out guessing the limits in those sections, where we were creating a table of values or we were looking at a graph, and it was an educated guess, but it was still a guess. And they promised us that when we got to the next section, they would give us some laws and some algebraic ways to help us with those limits. Now, the laws and the things that we look at today will not work on every single limit on the face of the earth, but they will help us with a bunch of them. And so we want to take advantage of the information in section 2.3. This is the really practical lesson about limits. This is a give me a concrete way to get the exact answer that I know I'm right for a limit. That's section 2.3. Okay? So to begin with, on page 84, they give me 5 limit laws. All right? The first one says, if you have the limit of two things that are being added, like they give you here f of x plus g of x, you can break that into two separate limits where you can do the limit of f of x and the limit of g of x separately and then just add those answers together. Similarly, law number 2 says the same thing for subtraction. If you have the limit of f of x minus g of x, you can find the limit of f of x by itself and the limit of g of x by itself and then subtract. Law number 4 says the same thing with multiplication. If you have f of x times g of x, you can find the limit of f of x by itself, the limit of g of x by itself, and then just multiply those answers. Law number 5 says the same thing for division. If you have f of x divided by g of x, you can find the limit of f of x first, the limit of g of x second, and then just divide those limits to get your answer, assuming, of course, that your denominator doesn't equal 0 because you do have a fraction. So if you go back to number 3, you have the limit of a constant times a function. And in that case, they tell you that you can pull the constant out in front and get it out of your way and just find the limit of the function. And then when you're done, excuse me, multiply by that constant. All right. So look at example number 1, if you would. For example number 1, we've got the limit of f of x plus 5 times g of x as x approaches a negative 2. Now, without those properties, this would be most miserable because I literally would have to come over here and say, okay, if I'm trying to find the limit as x approaches negative 2, I'd have to look at it from the left-hand side and from the right-hand side, so I'd probably have to plug in, maybe 3 values from the left and 3 values from the right, something like that. And to find each of those values, I would have to do f of x plus 5 times g of x. So like g of x is the blue function. Let's say that I'm trying to find the limit since I'm approaching negative 2. Let's say I'm approaching it from the left-hand side, and I'm going to use negative 2.1 and negative 2.01 and negative 2.001. I'm going to have to do 5 times negative 2.001 and plot that new value, and then I'm going to have to add that to the blue value, or I'm sorry, to the red value for f of x. That's just going to be a nightmare. And I'm going to have to do that like 6 or 7 times to be able to then try and guess my limit. Here's how those properties help me. According to those properties, I don't have to do that. According to those properties, I can say if I have two things that are being added, I can break that into 2 separate limits. So here's the limit of the first function and the limit of the second function. I also have that constant property that says if you have a constant times a function, you can pull the constant out in front and do the limit first. So now I literally can just look at the graph and say, okay, if I'm looking for the limit as x approaches negative 2 for f of x, come over here to the blue graph and say, okay, here's negative 2 right here. So as I approach negative 2 from the left-hand side and as I approach negative 2 from the right-hand side, both pieces of that graph are converging on one value. And the one y value they're converging on is 1. So I'm able to find the limit as x approaches negative 2 and find that it's 1. Again, remember we mentioned in section 2.2 that even though this function is defined otherwise at the point -2, I don't care what's going on at the point. I only care about what's going on as I approach that point from the left and from the right. What's going on at the point is completely irrelevant. So as I approached from the left and from the right, both pieces of that graph were converging on that one y value, and that one y value is +1, so I was able to evaluate that limit without needing to like plot 6 different values. All right. Similarly, if I want to find the limit of g of x as x approaches -2, then I could say, okay, g of x is the blue graph, so I can come over here to -2 and say, okay, as I approach -2 from the left and as I approach from the right, looks like both pieces of that graph are converging on one value. What one value does it look like they're converging on? -1. So I could say, okay, the limit of g of x as x approaches -2 is -1. Then use that constant rule to multiply it by 5, and use that addition rule to then add the limits that I found. And so I can come up with the exact value of that limit. Pretty straightforward process without having to go through, graphing combinations of functions and 6 different values and blah. All right, look at another one of those. B says find the limit of f of x times g of x as x approaches 1. All right, so again, if I didn't have these laws, I'd be over here taking the blue graph times the red graph at a bunch of different values from the left and from the right and creating maybe a green graph or something else to try and look at to evaluate my limit. So instead, what I can do is I can say, okay, according to law number 4, if I have two things that are being multiplied, I can break that into 2 separate limits, find the individual limits first, and then multiply. So let's find the limit of f of x, the red graph, as x approaches 1. So if I come over here as x approaches 1, what is the limit of my red graph? Yeah, it looks like it might be a value of 2. All right, then I want to find the limit of g of x, my blue graph, as x approaches 1. So as I approach 1 from the left-hand side and I approach 1 from the right-hand side, what does that look like that limit is? It doesn't exist. Why doesn't it exist? Yeah, the 2 sides of the graph are not converging on the same point. As I take the limit from the left-hand side, it's converging on a y value of -2. As I take the limit from the right-hand side, it's approaching a y value of -1. The limit from the left, -2, doesn't equal the limit from the right, -1. So therefore, that limit doesn't exist. So what's double does not exist? Still does not exist, right? So it doesn't matter if you multiply does not exist by something or add something to it or subtract something from it. If part of it doesn't exist, it doesn't exist. So that limit would not exist. All right, look at C. For C, we have the limit of a quotient. So we can use property number 5 that says I can break that into the limit of the numerator over the limit of the denominator. So let's start with the limit of f of x, the red function, at 2. Might actually be easier to look at the picture in the book because you've got all the pretty little grid lines in there on their nice perfect little graph. So if you look there on page 85, as x approaches 2 on your red graph, what does it look like your y value is? If you're looking at it on mine, you can kind of see it as well from the right hand side and from the left hand side. Are both pieces converging on one value? Yeah, it looks kind of like somewhere around 1.4, 1.5, something like that. It's just an approximate, so it's perfectly fine if you gave something in that vicinity. So from the left and the right, we were converging on the same y value, something around 1.4, 1.5. All right, then for our denominator, we've got the limit of the blue graph, g of x, as x approaches 2. So right here is 2. So as I approach 2 from the right-hand side and from the left-hand side, are both pieces of the graph converging on the same value? Yes, and what is that value? 0. So I've got 1.4 divided by 0. What's division by 0? Undefined. So even though I was able to find the 2 separate limits individually, because I got 0 in the denominator, remember they had given us that extra stipulation on law number 5 that g of x can't, that limit can't equal 0. That denominator can't equal 0 because, of course, that's undefined. So if your limit is undefined, then it doesn't exist. All right. On the bottom of 85 and continuing over to 86, they go through and they give us quite a few more laws that are really helpful. Law number 6 says, it is called the power law. If you take the limit of a function raised to an exponent, then you can use direct substitution, and you can do the limit first and then raise it to the power. So basically, instead of having the function raised to the power and then taking the limit, you can take the limit of the function first, get a numerical answer, and raise that number to the power. That's significantly easier. All right, over on page 86, law number 7 says the limit of a constant will just be that constant. The limit of 7 will be 7, no matter what you're approaching. So the limit as x approaches 222, 202, or 2002 doesn't make a difference. The limit of 7 is 7. The limit of a constant is that constant. Number 8 says the limit of x as x approaches a will just be a. Bottom line, what they're telling you there is that you can just use direct substitution. You can just plug in, and the answer that you get will be your limit. We called that in section 2.2 a limit like that. We called it well-behaved. Another name for that is continuous. So if you have a function that is just x, you can use direct substitution. It's well-behaved, it's continuous. That will give you the correct limit. The same thing is true in law number 9 when you have the limit of x to the n as x approaches a. Again, you can just use direct substitution there, and your answer would be a to the n. That would give you the correct thing. Now, number 10 is another limit law where I can use direct substitution, but it's under a particular condition that I need to be really careful of. All right, for number 10, it says the limit as x approaches a of the nth root of x will be equal to the nth root of a, meaning that you can use direct substitution as long as you meet a couple of qualifications. It says if n is even and n is a positive integer, but if n is even, we have to assume that a is greater than 0. And the key here is that they said greater than 0. They didn't say equal to 0. So here's what they are saying. The limit as x approaches a of the nth root of x, where n is a positive integer, will be equal to the nth root of a. You can just use direct substitution and go straight to your answer as long as a, what you get when you do that direct substitution, a has to be greater than 0. That's the stipulation. That's the only time it would work. So here's an example. Let's say that you had the limit as x approaches 2 of the square root of x minus 2. You do direct substitution for that, and you get the square root of 2 minus 2, meaning you get the square root of 0. You don't get a value greater than 0. You get equal to 0. Why can't that just be 0? I mean, the square root of 0 is 0. How come that can't be my answer? Why can that not be the limit? Okay, why does it have to be greater than 0? That is true, but why would that be? Think about what the graph of that function looks like. This is the square root function with a horizontal shift of positive 2, right? So if we come over here and we sketch this graph, looks like that. So what's the limit from the right-hand side? 0. What's the limit from the left-hand side? It does not exist. So anytime you get an answer of 0 or you get a 0 under that radical, that is this condition that you're going to be looking at. Yes, from one side, if that function is converging on a value of 0, then yes, from one side you're going to be able to find that limit, but from the other side that limit is not going to exist. So if you do direct substitution on a square root and you get 0 under that radical, flashing lights better go off for you. It is not well behaved. It would be okay if they just asked me to find the limit from the right. There'd be no problem with that. But if they had asked me to find the limit from the left, or they had asked me to find the overall limit, that limit does not exist. So I can only use that limit law number 10 under those very specific conditions. Okay? All right, and then the last one, number 11, says the limit of the nth root of f of x as x approaches a is equal to the nth root of the limit. All they're saying there is you can take the limit of what's under the radical before you actually take the square root or the cube root or whatever else it might be doing. So instead of having to take the limit of the whole radical, you can take the limit of what's under the radical and then perform your root. The reason for that is if you think about it, can't you rewrite every radical as an exponent? Right? Like if you've got the square root of something, that's the same thing as writing it to the 1/2, right? And don't we already have a rule that says if you have something raised to a power, you can plug the limit in and evaluate the function and then raise it to the power? So that's the same idea, right? Okay, so once we have those laws, they can help us to do example number 2. So for example number 2, it says evaluate the following limits, but justify each step with the law that you're using, okay? So we won't do this forever and a day, but we'll do this on the first problem or two that we do and on 1 or 2 of our homework problems, just to make sure that we understand what gives us the right to do the things that we're doing, all right? So for example 2, we've got the limit of 2x squared minus 3x plus 4 as x approaches 5. So the first thing that I want to do with that is I want to break that limit into separate pieces. And laws 1 and 2 are what gave me the right to do that, because that's what said if you have the limit of 2 things that are being subtracted, you can break that into 2 separate limits, find those limits individually, and then subtract your answers. Same idea with we had the 2 pieces that were being added. We can break that into 2 separate limits, find those limits first, and then go back and add the answers that we got. All right, the next thing that I could do is I could use my constant rule. Remember that constant rule said that if you've got the limit of a constant times a function and you want to take just the limit of the function, you can move that constant out in front so that you can evaluate just the limit of the function, and when you're done, multiply by that constant. So we've done that in the first piece, and we've also done that in the second piece where we pulled the 3 out in front. All right, so now let's evaluate this one piece at a time. Let's start with the limit of x squared. What law do I have that enables me to find the limit of x squared out of those 11 that we've just looked at today? 9, perfect. If I use law number 9 says that I can take that 5 and use direct substitution. It's going to be well behaved. It's going to be continuous. So I'm going to take 5 and plug it in, but to justify that, what gives me the right to do that is law number 9. All right, what law gives me the right to take 5 and just use direct substitution in for x? Close. 8, yes, law number 8 was the one that said that if you had the limit of x as x approaches a, that it would just be a. That again, I can just use direct substitution. It's going to be well behaved. It's going to be continuous. All right, and this last one down here, we have the limit of a constant. What's the limit of a constant? That constant, and what law tells me that? Law number 7, right. So we could say the limit of 4 is 4, and our justification for that would be law number 7. So now we can go through and combine what we have left. So 25 times 2 minus 15 plus 4 is going to give us 39. So here's the cool thing. We just used the 11 laws that they had given us to show that all polynomials are well behaved. So once I've proven something, then I can use that going forward. Now I can, if I come across a polynomial, I can say all polynomials are well behaved or continuous, so I can just use direct substitution with them. So that helps me when I get over to b, right? Because when I get over to b, I have a fraction. So if I use law number 5 gave me the right to say if you've got a fraction, you can rewrite it as the limit of the numerator over the limit of the denominator. In a rational function, what are my numerator and denominator? Like, what's x cubed plus 2x squared minus 1? A polynomial, right? And we just proved that all polynomials are well behaved. So I don't have to go through and do all those crazy steps that I just did over here a moment ago. I can just go through and use that I just proved, all polynomials are well behaved, as my justification for taking -2 and just using direct substitution into that cubic and getting -1, and then taking -2 and using direct substitution into that linear and getting +11. So now I just proved something else, right? If a rational function is just a polynomial divided by a polynomial, and I have a law that says, law number 5, I can break it up into the two separate limits, and I have the law that all polynomials are well behaved once I break it up, what did I just prove? Yes, that all rational functions are well behaved. There would be one exclusion to that. What would be the exclusion? 0 in the denominator, right. So what we can say is that all rational functions are well behaved within their domain. And that would be true for a polynomial as well, but a polynomial's domain is going to be all real numbers. So over on page 87, they state what we've just proved. If your function is a polynomial or a rational function, and a is in the domain of that function, then the limit of f of x will be equal to f of a as x approaches a. So basically they're saying that you can use direct substitution and get your limit. It will be well behaved. It will be continuous. Alright, so we get down to example number 3 and we're like, whoop whoop, rational function, going to be well behaved. I use direct substitution, and what happens? 0 in the denominator. So it's not well behaved. Okay, that means the limit doesn't exist then, right? Biggest mistake on this test is you do direct substitution and you get something that is not well behaved, and so you assume the limit doesn't exist. Just because the function is not well behaved does not mean the limit doesn't exist. Most of the functions we will work with this year are not going to be well behaved. That does not mean the limit doesn't exist. That just means I got to do something else. So at this point, what we would have done is we would have made a table of values, or we would have looked at a graph, right? Now we want to get some algebraic ways that we can attack this type of problem. Now you might remember from last year we did this type of thing where we said, take anything that you have learned in all of your algebraic life, anything that would modify what you are taking the limit of algebraically is fair game. So ignoring the limit, if you were just given x squared minus 1 over x minus 1, what would be your natural instinct to want to do to that? Factor and cancel. All right, let's try that. So let's factor our numerator. That's a difference of squares, so it would be x plus 1 over x minus 1. And then that x minus 1 in the numerator and denominator we cancel out. So what I'm left with is the limit of x plus 1. That's a polynomial, right? That's well behaved. So now I do have the right to use direct substitution to find that limit. So what would that limit be? 2. And sure enough, if I went through and I made a table of values from the left and from the right, it would converge on 2. If I look at a graph, if I throw into my calculator x squared minus 1 over x minus 1 and I get a graph, this is what that graph's going to look like. And sure enough, from the left-hand side and from the right-hand side, both pieces are converging on this value at x is equal to 1. And that is converging on a y value of 2. Now, you'll notice that there is a hole in the graph there because I did still have an undefined value from the original function. So I'm able to simplify that original function down to something that I can evaluate. It is still undefined there, but I don't care what's going on at the point. I only care about what's going on as I approach the point. Last year we harped about limit notation, and we mentioned that you can get the right answer on the AP exam, but if you don't have the right work to support it, that you can lose points. So we want to be very careful with our notation and everything that we do. So remember that with a limit, you're going to continue to write that limit notation until you actually take the limit, which is when you actually plug the a value in for x. So when we actually plugged our a value of 1 in the place of x right there, then we didn't write the limit notation anymore. But until we actually put 1 in the place of x, then we kept writing that limit notation. Now, caution about piecewise-defined functions. Piecewise-defined functions are not well-behaved even if all of their pieces are well-behaved. Even if they are made up completely of polynomials or rational functions or something else, you cannot assume that a piecewise-defined function is well-behaved. Here's an example of that. For example 4, if we take the limit as x approaches 1 of this function, I look at that and go, ooh, that's a constant and that's a polynomial, that's well behaved, I know what to do with that, so I can just use direct substitution. If I use direct substitution, when I put 1 in the place of x, it says when x is equal to 1, your answer is pi, so I would be tempted to say my limit is pi. That's not the case here though, right? Because for the limit, I don't care what's going on at the point, I only care about what's going on as I approach it, and pi only applies for the value at the point. X plus 1 is what I would need to use to figure out what's going on as I approach it. So if I were to think of this limit from the left-hand side, would I be using the top piece or the bottom piece of that function? The top piece, right. If I'm approaching 1 from the left, then I'm going to be using values not equal to 1, so I would be using that top piece. I'd be using x plus 1. That's a polynomial. I can do direct substitution. The limit from the left is 2. Same idea as I approach this from the right-hand side. If I approach this from the right-hand side, those are values not equal to 1. I'm using that top piece. That's a polynomial that's well behaved. So the limit from the left equaled the limit from the right. That limit was 2. It was not pi. So I cannot use direct substitution with a piecewise-defined function even if all of my pieces are polynomials. I cannot assume that it's well behaved. All right, look at example 5. If you were given example number 5, again, I try to use direct substitution, not well behaved, can't do it, but ignoring the limit, if you were just given this rational function and asked to simplify it, what would you do? Foil. All right, so let's foil the 3 plus h squared. That is not 9 plus h squared. 3 plus h squared is 3 plus h times 3 plus h, right? It's going to give you a trinomial, 9 plus 6h plus h squared. And then we had our minus 9. What would you do next? Cancel the 9's, all right? So I'm left with 6h plus h squared. You cannot cancel things that are being added. So like I can't cancel these h's right here. The only way that I can cancel those is if I factor the h out of the numerator, then I can cancel that h in the numerator and denominator. And then when I do that, what I'm left with is a polynomial that's well behaved. I can use direct substitution to get my limit. And again, being very particular about that limit notation, where we wrote the limit over and over and over again until we actually put 0 in for h. In the step where we put 0 in for h, we no longer put that limit notation. All right, the last one that they give us here is not a polynomial, not a rational function, can't use direct substitution. So something that we saw last year is that we could rationalize the numerator just like we rationalized the denominator. So I'm going to multiply by the conjugate, all right? The conjugate is when I multiply by, we've got the radical minus 3, I'm going to multiply by the radical plus 3. I don't change the sign under the radical, just the sign in between. It's like multiplying to get a difference of squares here. So radical square root times square root is just going to give me t squared plus 9. Radical times positive 3 and negative 3 times the radical are going to cancel each other out. Negative 3 times positive 3 gives me negative 9. And then down here in the bottom, we just carry both of those pieces along. In the top, the 9 and the negative 9 drop out, and then that leaves me with t squared that can drop out top and bottom, so that I've simplified this. Now, when I go to use direct substitution, I have to have a rule to be able to use it. And this is not a polynomial or a rational function, so I got to go back to my limit laws. So the limit of a constant is that constant. Down here, remember when you're taking the limit of a radical, you can take the limit of what's under the radical, and that's a polynomial, so I use direct substitution. Limit of a constant is that constant, and then we're able to find that limit, okay? So here's our homework for tonight. It's going to tell you on a whole block of these problems to give the laws. I'm only asking you to give the limit laws on like the first one or two. You can see for numbers 3 through 9, you don't need to keep giving those, okay?